Okay, we're going to be doing our last case of graph sketching, graphing a function given a graph. In this case, we're going to be going from f double prime all the way back to original f of x. So we're going to be moving 2 levels up. Here's our original graph. We have 2 asymptotes here at negative pi over 2 and pi over 2. We have a graph here, and I've noted a couple things. Remember that f of x and f double prime of x are related based on concavity. And that's how we find concavity of f. We look at f double prime. So keep that in mind. We're jumping back from f double prime to f. So we can see this function is concave down from negative pi over 2 to 0. There's an inflection point there, and then it's concave up from 0 to pi over 2. And we do have some asymptotes here for f double prime. So let's read this together. It says, following is the graph of f double prime, the second derivative of f of x. Use the graph of f double prime to sketch the graph of the original f of x. How can we do this? As noted before, we're going to focus on concavity, inflection point, asymptotes, and use that information to sketch the original. So step 1, where is f double prime of x positive? So why would we be interested in that? So let me go ahead and sketch that. And it's going to be above the x-axis from 0 to pi over 2. It's not to infinity. So change that real quick. Well, as I mentioned before, the original and the second derivative related based on concavity. Remember that whenever the second derivative is positive, we know that the original is concave up. Why? Concave up means that the tangent lines are increasing. It means the first derivative is increasing, so the second derivative is positive. So since f double prime is positive here, we know that for step 2, f of x must be concave up. Okay? So f of x is concave up on the interval 0 to pi over 2 because f double prime of x is positive there. For step 3, in the same way, where is f double prime x negative? Well, we can see it's below the x-axis from, again, it's negative pi over 2. So it's negative from negative pi over 2 to 0. And what that's going to indicate is if f double prime is negative on that interval, then f of x must be concave down. So for step 4, f of x is concave down on the interval negative pi over 2 to 0 because f double prime of x is negative there. So we figured out intervals of concave up and concave down. Where do we go from there? Step 5, where does f double prime of x cross through the x-axis? Well, we can see right there at x equals 0, and it's important that we say cross through, because if it touched but didn't cross through, that means that the concavity didn't change, so there wouldn't be an inflection point there. It indicates a concavity change, and therefore an inflection point crosses through. So for step 6, f of x must have an inflection point at x equals 0, because f double prime x crosses through the x-axis there. Step 7, where is f double prime of x undefined? Well, it's undefined at pi over 2 and negative pi over 2. So what does this tell you about the original? That means the original has undefined concavity, because f double prime of x is the concavity of f of x. The concavity of f of x then is undefined at x equals negative pi over 2 and x equals pi over 2, because f double prime x is undefined. Now I can tell you that for trig functions, a lot of times, if you have asymptotes for, say, the derivative or second derivative, the original probably has asymptotes too. That just comes from experience. And, the reverse is true. If the original has asymptotes, the derivative is probably going to have asymptotes there as well. Okay, step 9, plot points and asymptotes. It is likely, not definite, that there are asymptotes where the concavity of f of x is undefined, so I just talked about that. So the only other thing we can plot really is an inflection point right here at 0, 0. Sometimes I like to kind of notate what I've got there. We don't really have any x or y intercepts. We don't know what those would be based on the second derivative. But we do know concavity intervals. Remember, we determined that it's going to be concave down from negative pi over 2 to 0, and we determine it's going to be concave up from 0 to pi over 2. So it's going to go from concave down to concave up. So that's really all we can do, and we can form the graph of our original based on the fact that there's probably going to be asymptotes here, and it's going to go from concave down to concave up. So we're simply just going to do this. Go from concave down to concave up. Step 10, we just connect the dots, we curve around the asymptote, and it looks a lot like the original. Now, you might be thinking, why is that? Does that ever happen? And the answer is yes. I gave an example. If f double prime was x cubed, the original would be 120x to the fifth. That's a rule you'll learn very shortly. They both look about the same. One is just skinnier than the other. So yes, it can happen. And indeed, those shapes can wind up looking very similar, like basically a backwards S shape. So that's it for this example. We went from f double prime, and we went to the graph the original with the information we could conclude using concavity and inflection points and asymptotes to graph the original, which is going to look like the second derivative in this case. That's it for this example. Case 6 of going from f double prime to f. If you have any other questions about this, let me know.